Hello everyone. I would like to very quickly introduce Robotic Perception Group and the results we achieved in 2024. And as was heard, in CERC we are interested also in the solutions which extend beyond the scientific results. So I just want to give you an overview of some of the results which we actually in 2024 delivered to end users. And thanks to Thatcher and Edich projects, and those range from applications which connect machine learning and perception, and also robotic solutions. So for example, we develop automated pallet jack to supply pallets to bricklaying robot, which is actually was showcased in Night of Scientists and will culminate this year. And also long-term effort of Vláďa Smutný, which was supported by Thatcher and Edich, resulted this year in the final application of robot motion planning for welding of plastic tanks in cooperation with several industry partners. In 2024, we had also several scientific results, and for presentation today, we selected two of them, which are main work of our two PhD students who are finishing their PhD this year, and it nicely summarizes what they actually achieved during their PhD. Gabriela Šejnová submitted her thesis already in December, and Ondra Holešovský will submit it this month, hopefully. So I hope you will enjoy their work, and floor is yours, Gabina.
Okay, good morning. My name is Gabriela Šejnová, and today I would like to introduce our research on multimodal variational autoencoders, which was presented in October at IROS and which is also the main topic of my dissertation thesis. Multimodal variational autoencoders are neural network-based generative models that are able to learn some shared joint representation over multiple data inputs or modalities. So for example, language, vision, or action. And during inference, it's possible to omit some of these modalities on the input, and we can then generate one modality from the shared joint latent space based on the data inputs that are currently available. And also, since these are generative models, it's possible to also produce multiple output samples rather than just one solution, so we can have alternative solutions to the given problem. There are currently several state-of-the-art multimodal VAEs, but they have been mostly tested only on image and text data. And in our project, we wanted to see whether it's possible to apply these models also on robotics data or robotic manipulation task. So, and more specifically on the data set, it would be relatively easy to collect in the real world. So you can imagine raw camera images, natural language commands, and some robot motion trajectories where the robot performs the action. And so the goal was to systematically compare and evaluate the state-of-the-art models on this kind of data and perhaps find some possible improvements to this architecture. So we generated 36 synthetic data sets using a simulator. The data composed of raw camera images of the scene. We used a Franka-Emika robot with two-finger gripper, which was controlled using end effector positions and binary values for gripper closing and opening. And we separated the data based on the scene complexity, so either there was only one object or one or two distractors. We also separated based on how many actions the model had to learn in parallel, so either it only learned one action, such as lifting, moving the object left or right, or it had to learn two actions at the same time or three actions. And we also varied the positional variability of the object and the positional variability of the robot, I mean the amount of the variability, and the length of the task that it had to learn. Here we should play an example of the data. Okay, so it's very quick. This is the number of represented actions, just single one or two or three at the same time. This is the distractors, one or two objects or just single object that need to be lifted. Here, the length of the task, so the longest task was picking the object and placing it into a drawer and closing it. And here is the positional variability. Yeah, it was quick. And so on this data, we compared three state-of-the-art multimodal VAEs, which differ in the way they learn the joint representation. So there's an overview of the methods. The other parts of the architecture were kept fixed to make it a fair comparison. And also we compared two reconstruction loss functions. The standard mean squared error was compared with the sigma VAE loss, which is a newly proposed method by Ripken, which analytically computes the variance of the decoder distribution. And it showed promising results on single model VAEs, so we wanted to apply it to multimodal scenario. After training, we generated 500 testing trials for each dataset, where the model was always given the camera image and the natural language command, and it had to produce the trajectory. And we passed the trajectory to the robot in simulator and observed whether it fulfilled the task. And the numbers here are the reported accuracies of how many times the robot fulfilled the task out of the 500 trials. As you can see, the sigma VAE loss function performed the same or better than the mean squared error in all of the cases, so that's quite a clear enhancement of the model's performance. The MVAE model is most robust to all the criteria that we observed, the positional variability, scene complexity, and also the task length. However, the accuracies for the more complex scenes with one or two distractors were always very low, which indicates that the mapping between the pixel space and Cartesian space of the robot is still quite a challenging task to be done in an unsupervised fashion for the model, so that should be our focus in the future research. And since this research, we also focused on developing transformer-based multimodal VAE, our own approach, which we compared on this data with the state of the art, and that's also my other part of my dissertation. So that's all from me. Thank you.
Are there any questions? Joseph, please pass him the mic.
Did you assess generalization of the approach to like new objects or new situations, or how do you think about this?
Yeah, we are thinking about it. Of course, we had to search through many different variability of the model. We were looking for some functional scenario where the model had some optimal latent space size, and there are many parameters which we had to fine-tune. We also altered the objects, but some broader study that actually really defines what is possible and not needs to be done yet, I think.
Okay, thank you.
Hello, my name is Holešovský, and I'm going to talk about our paper MovingCables segmentation method and dataset by me, Radoslav Škověra, and Václav Hlaváč, published in the journal IEEE Robotics and Automation Letters. It addresses the following problem. Imagine there is a scene with complex tangled cable clutter. This problem is hard for perception or for cable segmentation or cable instance segmentation. Humans simplify this problem by grasping the cable of interest and moving it. This motion basically simplifies the perception. We follow a similar idea in this work to segment moving cables. We approach the problem by first recording a data set of moving cables. In this case, it's a yellow hose with ground truth optical flow and instant segmentation masks. We painted UV fluorescent cylindrical markers using a transparent paint on the hoses, and switched or alternately switched between UV lighting and white lighting. This enabled us to collect both or simultaneously collect images of both the fluorescent markers and the marker-free cables. We recorded multiple different cable configurations with multiple different motion types. When we had this data, we post-processed them to obtain more complex cable scenes. Chroma keying technique segmented the blue screen background and the green poking tool. Our custom marker detector detected the UV fluorescent markers and tracked them. These marker tracks enabled optical flow computation by interpolating between these marker tracks. Finally, compositing multiple single cable clips on top each other and changing the background gave us more or images or video clips of more complex scenes. This is a sample composite clip of the MovingCables dataset. You can see the color images at the top left, then the optical flow ground truths, the instance segmentation ground truths, and the bottom row depicts optical flow predicted by several methods we evaluated on our dataset. The methods segment MovingCables by first predicting the optical flow and then thresholding it or thresholding its magnitude by a fixed constant threshold. When the optical flow at a certain pixel is larger than this threshold, the pixel is labeled as moving cable. In these figures, it's depicted in red. These are some state-of-the-art optical flow predictors we evaluated first on the dataset. Then we chose the mask flow net to improve, and we improved it first by retraining it on traditional optical flow datasets using a different loss function. This gave us MFN probe with improved accuracy on the MovingCables test set. Then we utilized the MovingCables training set to fine-tune the mask flow net network on a mixture of traditional optical flow data and or the datasets and our MovingCables. This improved the mask flow net FT means fine-tuned. And finally, we did the same thing with MFN probe, which gave us the best method overall on MovingCables test set. These are some real-world samples where we evaluated all these methods, and you can see the MovingCable segmentations in green. Our methods currently have the limitations that they assume that there is only a single cable moving in the scene. This week we submitted another paper which addresses the more general case where the grass cable can perturb neighboring cables and therefore causing multiple moving cables. So that's like a submitted work. And maybe one last thing to note is that this SAM plus Dino method, which is segment anything and Dino feature selection, is not very good at segmenting like cluttered cable instances. Thank you for your attention.
Thank you.
So good morning, everyone. My name is Libor Přoučel. I'm heading Intelligent Mobile Robotics. So I have 1 minute for just brief intro. So what we are going to present now are two, let's say, reasonable, nice results we achieved last year. One focuses some parts of vision-based navigation solution. The other one, let's say, deals with some kind of optimization or maybe more computational geometry problems. Moreover, we achieved 2 more journal articles, from one of which was in D1. The other one by Scopus is Q2. We had 3 conference articles, 2 Core A, so that was Iros, ICRA, and the other one has not been assigned some grading so far, but it's in the process. At the moment we have 4 running projects. We participate on RoboProx project, and beside this, what is listed on this slide, we also defended 2 PhD students, so we've got new 2 doctors through the last year, where one of the theses is in the closest selection for Werner von Siemens Prize for Best PhD thesis. So now I'll give floor over to Tomáš, who is going to present the first paper.
Okay, so good morning. Today I would like to present to you our paper on model-free ranking for visual place recognition with deep learned local features that was accepted into transactions on intelligent vehicles. We solved visual place recognition task, which is task of searching for the location from which a query image has been captured. Individual locations are usually represented as a database of image, so we are searching for the most similar image from a database, which is similar task to image retrieval. Because compare a query image to all images in a database in some exhaustive manner is not always possible, the recognition is divided usually into filtering and ranking stage. Filtering stage uses some faster method that preselects the best candidates that are compared more in detail in the ranking. And in the ranking is very often used spatial verification of local visual features matched between images. And there are two approaches for spatial verification. Model-based systems tries to estimate some transformation between images and verifies the consistency of found model. And model-free approaches tries to compute the similarity directly from feature matches. And in our paper, we focus directly on this model-free ranking stage. And the possible applications of visual place recognition in mobile robotics are mainly some basic localization, and also visual place recognition is often used in SLAM system, simultaneous localization and mapping system, for detecting loop closures, which is visiting the same place that then triggers some optimization of a map. Our work was inspired by a previous system developed in our lab by former colleague Luis Gomez Camara. That system used deep learned local features extracted from convolutional neural networks. This system also used the was recognition divided into two stages. And in the ranking stage, it used a ranking based on concept of anchor points, and this system achieved state-of-the-art performance few years ago, and it evinces high robustness to varying conditions, which is important property for possible applications in long-term autonomy. So we are motivated by this system and focused on the other possibilities for ranking methods. We designed 3 new approaches, and these approaches were integrated into a new system that used in a ranking stage D2net local visual features. And this new system was compared to several state-of-the-art systems. The experiments were performed on 6 public datasets for long-term autonomy, and our main achievement was that one of our methods combined with another system, mixed VPR, used in the filtering stage for the preselection of candidates. This system achieved best overall results from all tested systems. So that's quickly about my research, I think.
So hello everyone, my name is Jan Mikula, and I will present a software paper called TriVis. It's a versatile, reliable and high-performance tool for computing visibility in polygonal environments. So in polygonal environments, we can have multiple types of queries. For example, we want to determine visibility between 2 points, or we have a point and a direction, and we want to compute intersection point with the environment, or we want to know all visible vertices from a given point, compute visibility polygon, which is the whole region visible from the point. We have 3 types of visibility graphs, and sometimes we might be interested to compute all these queries under limited range constraints. So here's an example of efficient algorithm to compute visibility polygon. It's called triangular expansion algorithm, and it operates on triangular mesh. And as you can see, it kind of rotates around, it expands triangles, and as it does so, it computes the polygon. So here comes our contribution. We implemented TriVis, which is a new standalone, versatile, reliable, and high-performance tool. It's a C++ implementation of the triangular expansion algorithm, or the TEA, and it has been adapted to all the visibility queries that I mentioned at the beginning. We did some improvements. So, for example, for 2-point visibility and ray shooting, we improved the query time from nh to n, where n is the number of vertices and h is the number of holes. Then we have efficient limited range queries, which means we expand minimum triangles under limited visibility. We have rapid point location queries, due to bucketing technique. We compared our library to Seagull, which is kind of the default option in computational geometry. It's a computational geometry algorithms library. And we found out that we are more robust, that the implementation in Seagull are crashing and they are infinitely looping, and it doesn't happen in our case. And we are also about 10 times faster than Seagull. So here's the example of the improvement where we have directional TEA, so we are only expanding triangles in the direction of the ray, which improves computational efficiency. Here are limited visibility queries, where you can see that yellow are the expanded triangles, and as the visibility is smaller, we expand fewer triangles, which again improve efficiency. We tested our library on a dataset of large polygonal domains, which had around 8,000 vertices and 600-700 of holes, so quite complex environments. And here are the results of runtimes. So we recorded initial time and preprocessing time. Initial time is constructing the environment. Preprocessing is some official preprocessing operations, such as constructing the triangular mesh. And then query time is the average query of computing visibility polygon. And as you can see, when we combine the initialization and preprocessing time, TriVis is much faster than some Seagull variants that we tested. And especially when looking at query times, TriVis takes just about 9 microseconds, whereas the most robust Seagull implementation takes 142 microseconds, so which is at least an order of magnitude of improvement. So to conclude, TriVis is performant, it is reliable, it avoids crashing and infinite loops, and it delivers consistent output, which Seagull sometimes does not. It's versatile, it has user-friendly API for all the queries, and it is independent of external libraries, which means that all dependencies are bundled with the code, and it's freely available for private research and institutional use. And it's on GitHub. And that's all from me, and I'll be happy to answer any questions.
Okay, so let me say something about applied algebra and geometry group in the meantime while they set it up. So we work in computer vision robotics, deal with things which are related to basic research, mathematical understanding of the topics, but also applied things leading to understanding and developing things in computer vision. The group originally included also Josef Ševic, but he has established his own group this last year, so we are currently basically led by me and with Torsten. And this year actually we have a very important achievement, which was Torsten's paper, which received a prize at CVPR for the best student paper, so this is a really outstanding achievement, and Torsten will talk about it. So first you will hear about 2 results from Torsten, and I will add another result from my group. Torsten.
Yep, this is actually work by Sehao Yu, who's currently actually visiting. So I'm going to present 2 papers, both in the same field. The first one will take slightly more time, the other one's quicker. So we are looking at the problem of 3D reconstruction. So we're given a set of images, and we know where they were taken in the world and the intrinsic calibration, and what we would like to do is build a 3D model of the scene. And traditionally, this is you either reconstruct a point cloud or some triangular mesh. Then you can render it from new perspectives. You can use it for pathfinding for robots, and so on and so on. And about 3 years ago, something called neural radiance fields popped up, where the idea is you don't explicitly represent geometry, but everything is represented implicitly through the weights of a neural network. These are results that I presented last year here at CACORR from some work by Jonas Kohanek, where you can see that this implicit representation can give you highly photorealistic renderings or representations of the scene. These radiance fields work as follows. So if we want to render an image and we want to get the color for a pixel, we shoot a ray through that pixel, sample points along the ray, and for each point we do a lookup in the radiance field. So we apply a neural network, compute a color, and then we aggregate the colors. However, this is highly inefficient. Modern GPUs are not very good at it, which means rendering times, training times are rather slow. Like soon after neural radiance fields, about a year later, something called 3D Gaussian splatting was proposed, where the idea is we represent the scene through hundreds of thousands or millions of 3D Gaussians. So each Gaussian is defined by a position, covariance matrix that defines the sphere, and some view-dependent color function. And the nice thing about these is you can render them very efficiently by projecting them into the image, which can be done using traditional rasterization pipelines, which is essentially the thing that GPUs were made for in the first place. So you can do rendering very quickly, you can do it real time, even in a browser. So this approach can, again, like build 3D models that are photorealistic. So this is a rendering of a reconstruction, not the actual images. However, the original formulation has a few issues. So this is what happens if you zoom in into the scene or change the focal length. And as you can see, structures are much thinner or much thicker than they're supposed to be. And that's not a coincidence, that's by some design choice of the original algorithm. So the idea is we have a 3D Gaussian, 3D object which we represent by a sphere in 3D, which gets projected into an image and results in a 2D Gaussian. And this Gaussian splatting method tends to generate many small Gaussians in order to be able to represent fine details, which in turn lead to numerical and other issues during optimization. And one thing that the paper does, although it's not mentioning it, is it's using a 2D dilation to ensure that each Gaussian is projected to at least a pixel, so that you don't have Gaussians that don't have contribution to pixels. And that makes training better, but also introduces problems. So here's one example of a dilation artifact that occurs if you're zooming out or moving away from the scene. Because something that should be projected to less than a pixel, all of a sudden, due to this dilation that enforces that it projects to a pixel, looks much thicker. So the spikes of the byte should be much smaller, but you get them thicker because you enforce that they project to that they cover at least a pixel. As a side effect, what this can lead to is degenerate Gaussians that are infinitely thin, and that still project a pixel because you enforced it to project to a pixel. Similarly, if you have these very thin Gaussians and you zoom in, you see these very thin structures that are not realistic. So you get these ghosting artifacts here in the background. So the observation is that like small Gaussians, like they are needed, they represent fine high frequency details, but they also these high frequency details cause problems. Luckily, there's a principled way of handling two high frequency details, which is to apply some form of low pass filtering. And you can do this both in 3D by enforcing that the Gaussians have a certain minimum size that depends on your training data, and in 2D by simulating like the physical capturing mode. Here's a comparison. On the left, you see the original Gaussian splatting formulation that does not take the size, does not do low pass filtering. On the right, you see our formulation. As you can see, we are able to like recover the scene in much more detail. We avoid many of these degenerate effects. And as always, code is publicly available. Do you have any questions?
Yeah, so let's open the speaker.
I'm going to talk. Good. Okay. So the second one is also about 3D Gaussian splatting. The paper is called Wildgaussians. It's with Jonas Kohalnik, Song Yu-Peng, Susanna Kukulova, and Mark Polyface. It was presented at NeurIPS last year, which is one of the bigger or the biggest machine learning conferences. What we're looking at is, so all of the results that I showed previously were obtained on like nice data in the sense of that the images were captured with good cameras, a lot of detailed attention to detail went to the image capture process, and they're all captured under roughly the same lighting conditions. If you want to reconstruct images, say from scenes from, say, images downloaded from the internet, you actually don't have these properties. You have images taken under different conditions, you have images taken with different cameras, you have occluders and whatnot. And we would still like to be able to reconstruct it, and we would also like to take advantage of the fact that we have images under different conditions, so that we should be able to relight the scene as we wish. So as I mentioned, we go from a setting where we have control over the image capture to one where we don't have control. So we have to deal with images taken under different illumination conditions. We have these occluders, especially in front of landmark buildings, there are a lot of tourists that get captured. And if we don't model it, we'll get something like this. The colors are a bit blurred. They are not fully consistent, so here in the bottom you see things that are darker than they are supposed to be. You get these occluded things that come from effects where people were in the picture. So this needs to be handled. We handle them using two effects. The first one is handling these appearance changes. We're not only modeling like the standard Gaussian, but equip each Gaussian with a learnable vector that effectively encodes how the Gaussian would look like under different conditions. And we also compute a learnable vector per training image that essentially encodes what are the conditions in this image. So it's taken at dawn, during the day, at dusk, and so on and so on. And by combining these two embeddings and feeding them through a neural network, you can essentially compute a function that takes the original color function of the Gaussian and maps it into something else. It's a fine transformation of the color function. So you get a new set of Gaussians where the positions, covariances are the same, the color function has changed. And that allows you to render the image under different images under different conditions. And this embedding space of the images is rather smooth, so you can actually do meaningful interpolations in these appearance space. So you see two target images, and we smoothly interpolate in embedding space and then render the scene with different embeddings. The other thing is handling occlusions. That's mostly a problem during the training process. We have images where there are occluders and you don't know a priori where the occluders are. So what it amounts to is that you have an image, training image, where there's a person in it. Your rendering ideally should not have a person in it, and you need to be able to handle this when training the representation. And we do this by extracting a set of pre-trained features, dino features mentioned in one of the previous talks. And based on the dino features extracted in the image and the rendering, we try to get an estimate of which regions in the image are likely occluded, have a higher uncertainty, so that if we compute a loss between those two images by essentially computing a color similarity per pixel, we take this uncertainty into account and try to not weight pixels with a high uncertainty. And this uncertainty prediction is trained during the reconstruction process. Here are some results on a dataset with lots of occlusions. This is the standard Gaussian splatting formulation, where you see there's lots of occluders because it doesn't handle them explicitly, and these are our results, where you can see that we are successful in removing these occlusions. Here's the same results that I showed before. This is TriVis found in Rome, where we're able to A, remove all occluders, and B, we can render the scene from new viewpoints under different conditions. So we can create these nice fly-throughs. So this works quite well, but it requires that the scene is captured under different conditions. One of the things that we're currently looking into is, can we actually train such a model where we can change appearance without having training data under all conditions. So assume that you only had captured the Davidsgar campus in summer. Can you actually predict how it would look like in winter or in different night conditions? The first thing that we did was we looked into diffusion models to be able to predict how a scene would look like under different conditions. Not quite working as we hoped it would be, so it's ongoing research. And yeah, if you have any questions, please feel free to ask.
Questions? If not, then what is nearly impossible in this research domain? What could be, for example, topics for the next PhD thesis?
I think like handling these predicting appearances, realistic appearances, in a way that generalizes is like more challenging than we thought it would be. And I think you could spend a PhD on this. And I think it would be interesting because if you can do this, you can create quite photorealistic simulators. You could, like, you would reduce the amount of data capture you would need to build simulators and so on and so on. So I think it would be worthwhile.
Okay, thank you.
Okay, so I will present a result which is a basic research, mathematical, with my colleagues Tim Duff, Kathleen Kohn, Anton Lekin. This has been published last year in International Journal of Computer Vision. This is a top journal with simply one of the best in the field. And the result, the work is about 3D reconstruction. So the problem is to have images, as you see on the panel on the top left, and coming out with a 3D reconstruction, which was shown below. So this is the basic problem of computer vision. There's many applications like 3D reconstruction, which you know from Google Maps and elsewhere, or movie industry, where you want to combine a synthetic world with a real world and produce special effects, and elsewhere. So the problem here is to take a set of images and create a 3D reconstruction of the scene, including 3D points and including camera poses, and have basically a geometric understanding of what has been seen. This is classically solved by kind of a pipeline which first takes images, then using machine learning establishes kind of tentative matches between those images, which are of course not perfect. And in order to arrive at something which makes sense, it uses a small computational, or small, I mean, many computational kind of problems which are based on finding, or which use actually the principle to find the largest consistent subset of those matches, which somehow fits to the geometry of possible geometry of cameras. And our work is about these problems, how to find which problems are there and how to compute them and how to assess how difficult they are. So this is a basic problem of computer vision, the basic problem of understanding what we can see, what we can reconstruct, and how we can deal with that. So let me say what this minimal problem is, just an example. So you can imagine we are estimating some model from data, and in this particular case we have a model which is a line, and the data which are just points in space. And this is given us, this is determined by solving kind of two linear polynomial equations. It's a very simple problem, and the minimality means that we have exactly as much data to uniquely determine what is necessary. And of course, what is not minimal, for instance, if we don't have enough data, so we would have too many models, infinitely many models, or we have too much data, so that there is no model which would fit them, like 3 points in the plane would not be explainable by a single line. So the problem here is to somehow look at these problems, which are 3D reconstruction problems, and we say they are minimal if the number of solutions to these problems is a finite non-zero number, smaller than infinitely, for a generic, that means in human kind of understanding, random the input data. And in this particular case, we are solving for something like a pose of the camera and pose of those 3D points in the space. And the fundamental research question is, what are these problems? So let's say we have 2 cameras, 3 cameras, 4 cameras, and so on. We have some problem, we have some points in space, some line in space. These points may be incident to those lines, and the question is, what arrangement of points and lines in space and cameras can give us problems which are exactly solvable and can be obtained by this approach. So there was a result which we published in 2019, which found that if you see all these points and lines in all cameras, and if you use all the knowledge which is there, so there are exactly certain minimal problems, and not more and not less. And this result received that time Best Student Prize at ICCV, which is something similar to what Torsten received this last year. Now, the new result, which actually I should present now, is going beyond that. The question is now, what if we don't see everything in every image? So what if we don't detect some point in some image or some line in some image? What if we miss something? And for instance, this is the case, right? So we have 3 images, and there are 4 points in space. There is 1 line in space, but in one image we don't see 1 point which is on a line. In the middle image we see everything. On the right image we don't see the line, or we don't detect the line. So this is very realistic scenario, which happens very often, but the scenario is much, much more complicated than before. Before, we could show that if there are too many observations, then we can't really find any model which would explain them. And now we are in a much more difficult situation when there is infinitely many such problems, because you can always add some more views and remove some points, and you can balance already like how much you see and how much you want to compute. So this opens a large space of problems. So we started with something which is simple as possible, but already something more than before, and we assumed only to have 3 views. Still, this is very hard, still infinitely many problems, and in order to be able to deal with that, we somehow added some technical condition that these lines can be somehow adjacent to like maximally 1 point. So this was technical condition. So it doesn't get all things in 3 views, but it gets many, many things in 3 views. Still, it's hard. The result here, which we got, is that we completely classify all manner of problems for these 3 calibrated views with that technical condition, and we found that there is 74,575 classes of the problems. Each class is infinite, but these classes can be described. And not only can be described, we can also somehow assess the difficulty of each of the class, which is basically related to the number of solutions which each problem in the class has. And this is some kind of a table which shows that some of the problems are simple. There are many of simple answers, relatively simple. Some of these problems are very hard. There will be thousands, tens of thousands solutions. So these problems are hard and are not really practical. But these guys which are here are practical. So we could classify things which don't have any incidences. So this panel shows kind of pictures, like the top left says, well, there are 3 images. Each image sees 3 points and 1 line, and so on and so on. So these guys are problems which don't involve any points sitting on lines, for instance. And you may see the numbers below these tiles. They show basically how difficult the problem is. So if something has a number 80, it's relatively easy. If something has number 1456, it's much more difficult. Okay, so the point is this. So we explained many problems in geometry of 3 views, which really actually extended a long list of research or trifocal geometry, which was here, like 100+ papers which appeared in past. So we basically gave much, much more before. Humanity knew something like 66 problems of this type before, and now we have 74,000 problems. So we know much more now than we knew before. Thank you.
Questions?
Okay, so thank you very much. I'll present some of the results of the Intelligent Machine Perception group. We've selected 3 publications out from the list of all the publications. I would like to also mention, I think, other kind of notable thing. We have 3 PhD students. One of them defended already in December, and 2 have submitted the thesis. So the 3 results are here. I will start with the first one. So we do research in computer vision robotics, and more recently in machine learning for life sciences. So we'll have in each of these 3 domains. I will start with the first result. This is a result of Tomáš Souček, who has just submitted a thesis, already started a job at Meta in Paris. And this work was published at the IEEE transaction of Pattern Analysis Machine Intelligence, which is one of the top journals in computer vision. And the problem we are looking at here is, if you are, typically if you want to set up a robot to do something, you usually have to manually define what the success is. Whereas ideally, we like to have the robots to really be able to learn from, say, videos, how the world, how the actions of the world are changing the objects. So here we are looking at this problem, but more from the learning side, from the computer vision perspective, where we are looking at how, trying to learn how people, when they interact with the world, how they are changing what we call states of the objects, like having an apple which is whole or then being cut. So we've developed, the problem setup is that we have a large collection of instructional videos where people are interacting with the world and changing the objects, achieving certain tasks. And our objective is to learn a set of classifiers which will understand in what state the object is. And also ideally the action which is changing the state of the object, like cutting by knife is changing the state of the apple. I'd like to learn this automatically without any annotations. So that's the objective, because the annotation is expensive. The problem is difficult because we have, there's a large variability of the visual world. Videos are long, you can imagine someone is showing for 10 minutes how to do something, and there is a lot of noise. Our key contributions, we designed a self-supervised learning algorithm which can learn this automatically by incorporating several constraints on this problem. I will not talk in detail about this, and we've investigated different architectures for this problem. Here are, I think, the 4 examples. The spoiler is, this one is the best, but we have sort of computational results for this. We've applied this on several public data sets on which we evaluated how the technique works. It works significantly better than what is currently available. The results are not just a couple %, the difference is quite large. And now we are looking into applying these models on the real robotic setup. This is ongoing work. So the second work, which we would like to show, will be shown by Katerina Zorina. This is more in robotics. This is work which has been published at the RAL journal. We like to publish there because of a very quick turnaround in the publications, and it's a good review process. Katerina, please.
Can I switch the slide?
I'll switch it for you.
Okay. Okay, so my name is Katerina, and today I will present, there's my picture. I will present a temporal consistency for object pose estimation from images. The main motivation for this work comes from robotics. So on the next slide. Thank you. You can see the example of Atlas robot from Boston Dynamics manipulating the object and putting this, probably a car part, to some designated place, and stable and temporal consistent object pose estimation is really important for object to not have some additional unexpected motion. And another motivation is handover from human to robot. So here it's also very important that the prediction of the object that robot wants to grasp is really consistent, because for example if the object is suddenly 20 centimeters away and robot would reach for it, it can potentially harm the human. And those are not empty words, because the other day in the lab I was doing some experiment, and when the object is fully occluded by a piece of paper, the robot really moves suddenly, and if not quick reaction of my colleague could have been painful. So the problem formulation for our work, no, actually not yet, the main goal of our work, no, the next slide, but I just started talking, but yeah, anyways. The main goal of our work is to create the temporally consistent object pose estimator. And here are some more examples. You can see the estimation of off-the-shelf algorithm COSI-pose on 3 frames that come from camera attached to the robot hand. And on the left image, okay, so the COSI-pose estimation is shown in red contour. So this is the object pose. And on the left image, when the object is clearly visible, the estimation is fairly good. But as soon as we have partial occlusion of the object, the contour is off, and also the rotation, for example, in the right frame, is really off. And if we plot this in time, we plot the next slide, the rotational component in time. This is a 1D representation of rotation. It's really stable while we see the object, but as soon as it's occluded or something else wrong happens, there is a lot of noise. And our goal is to reduce this noise and have a more consistent estimate. Next slide. Thank you. And have a more consistent estimate for better control of the robot. Next slide. The problem setup is that we have the robot with camera fixed on the robot hand. And next slide. We want to perceive the object pose or the transformation from the camera frame, that is a blue and green arrow here, to the object frame, which is red and green arrow. And we do this in time, so we'll receive a stream of frames from the video, and the robot can move, and the object can move. But since we know that camera is rigidly fixed on the robot, we know the pose of the camera, and the task is to find the pose of the object that would be consistent over time. And our approach to this is to build, to combine probabilistic models and motion models. So for motion models is that we make some assumption about the object, so how much the object can move, and for example, if it moves with certain velocity, it will continue to move with the same velocity in the next frame. And also we represent the uncertainty of our current object pose estimate. So for example, in the very first frame, when we just have the prediction from off-the-shelf 6D pose estimator, we know that it can be quite not accurate in the depth dimension, because the difference between the object when it's closer or further from the camera is not that big as when it moves to the side. So here you can see that the uncertainty in the depth, so from pointing along the ray, pointing from camera to the object center is higher. And also if we don't see the object, our uncertainty about its pose will grow over time. And in our method, we will discard everything where the uncertainty of the current estimate is too high. We'll just discard those predictions. So next to some examples. In the first example, you can look on the mustard, and when it's partially occluded by the box, the cozy pose, so the red contour prediction, is high and less accurate, while we maintain more stable prediction. And the next example is the task when robot is tasked with tracking the object. So the robot hand will follow the object when the object disappears behind the paper, so the full occlusion. Cozy pose method cannot predict where it is, but since we have this assumption that object stays the same or moves with the same velocity, we can still predict its pose and have this more stable control. That's it from me. Thank you.
Thank you very much. So, Katarina's a PhD student in our group, and she's finishing writing up her thesis, so which is going to be happening soon. And the last talk, which is going to be given by Roman Bushuiev, who is also a PhD student in my team, but jointly with the team of Tomáš Pluskal at IUCB Prague, which is just across the street. It's with organic chemistry and biochemistry. And he's going to talk about actually a combo of two papers, one at NeurIPS, which is one of the top machine learning conference, and the other one which just got accepted to Nature Biotechnology Journal, which is one of the top journals in biology with a very high impact factors for us. It's like one of the first achievements in this area of this caliber, so we are very happy about this. And Roman will tell you more about this very interesting problem he's looking at.
Hello everyone, my name is Roman, and I'm going to, as Joseph said, I'm going to present briefly two papers, and both of them are on machine learning for the discovery of new molecules from nature. So the nature is truly incredible. Living organisms act as real chemical factories, producing a diversity of molecules, and each molecule has a unique structure and function. So here you can see some examples. So this molecule on the top left is luciferin, which is characteristic for this emission of light in fireflies, for example. This cinnamaldehyd, this small molecule in the bottom left corner, is responsible for this very nice smell of cinnamon. Or this lycopene long molecule actually colors tomatoes red. Or as you may know, this very well-known antibiotic penicillin actually comes from fungi. So and obviously there are many, many more molecules in the nature, but the question is how many of them do we actually know? So unfortunately, it turns out that we still don't know most of them. Even in a simple organism such as E. coli bacteria, we have not yet discovered more than 80% of molecules. So in more complex organisms such as plants or a human body, these numbers are even higher. So now the question is, how can we even discover new molecules? Well, and the most prominent technique is mass spectrometry, and the workflow can be summarized roughly as follows. So first, a biological or environmental sample is prepared, for example, by grinding or mixing it with something. In the second step, it is analyzed in a mass spectrometry system, which, roughly speaking, measures masses of individual molecules and also masses of their fragments, enabling to kind of produce a unique fingerprint for each molecule, known as its mass spectrum or tandem mass spectrum or MSMS in short. And then the ultimate goal of mass spectrometry is then to decode these fingerprints into complete molecular structures, allowing for the discovery of new molecules. But unfortunately, in this pipeline, it's a main bottleneck to decode molecular structures from mass spectra, and even, let's say, state-of-the-art machine learning models are still not able yet to annotate more than 90% of mass spectra with molecular structures. And this is exactly where our work comes in place. But instead of directly predicting molecules from mass spectra, our approach is based on 2 steps. So in the first step, we kind of train a machine learning model to first understand the mass spectra, or let's say to make sense of them, or in other words, to predict some meaningful representations of mass spectra. So in such a way that they encode some properties of molecular structures. And let me just briefly introduce what these representations are. So similarly to how ChatGPT is trained to understand text mainly by predicting mask and parts of sentences, we also train a neural network called DREAMS, which is trained to understand mass spectra and the underlying molecular structures, mainly by also predicting mask and parts of mass spectra, some signals in this mass spectra. And as a training data, instead of the whole internet, which let's say was used to train ChatGPT, we use something very similar to the internet, but in this world of mass spectrometry, which is a huge repository of mass spectrometry-based experiments deposited from different biological or environmental studies. For example, some clinical studies of blood, or some beer analysis, or some, let's say, plant extracts, and so on. So in total, this repository is comprised like thousands of such scientific experiments and with millions of mass spectra in them. So indeed, once we train this ChatGPT-like model to unmask hidden signals in mass spectra on these millions of training examples, we observe that it derives some representations of mass spectra that capture molecular structures exactly as we wanted. And this is shown on the right. So each point here is this representation of a mass spectrum, and colors denote some molecular properties. And we can clearly see that even though the model was never trained on molecules, only on mass spectra, it can separate, for example, carbohydrate molecules shown in green from the molecules with more exotic chemical elements shown in pink. So and why is this representation so interesting for us? Well, because having them, we can kind of start navigating this whole internet of mass spectrometry data. So what is shown here, each node is again a representation of a mass spectrum, and the edges somehow connect them so that it tries to cluster similar molecules together. And in this particular example, we can see that we can kind of form a hypothesis that psoriasis disease can be somehow provoked by fungal pesticide. And to the best of our knowledge, this hypothesis hasn't been established before. But this is just one particular example in this huge internet of mass spectrometry data. If we look at other examples, we can find potentially new cancer biomarkers. In other words, molecules that can help identify cancer. We can also find some interesting plant-specific metabolites which seem to be abundant across different plant species. So further, in the same work, we also show that these representations can not only help to, let's say, connect different studies or molecules together, but also to predict some properties of molecules. So not yet complete molecular structures, but some interesting properties such as drug likeliness, for example, or some molecular complexity, which is interesting because it's a potential measure to search for new life beyond Earth when mass spectrometry is implemented on the space stations. So regarding the next step, obviously we are not the only group in the world working on this problem. Actually, there are many people in the world having the same goal to decode molecules from mass spectra. But unfortunately, currently it's really challenging to compare different methods across different groups in the world, and actually to measure progress in the field. So therefore, we first decided not to develop a model, but first to establish a community-wide benchmark so that whole community agrees how we should validate the models and kind of proceeds further together. And I will just briefly introduce the main components of this benchmark. First, it contains the largest public data set of mass spectra labeled with molecular structures. And actually, the big part of this data set was measured in our group at IUCB Prague. The second component is a new non-leaking train test data spread. What it means is that if we see that some method performs really well on our benchmark, we really want to make sure that it's not because it, let's say, memorized the training dataset, but because it really generalizes to the discovery of new molecules. And the last part is predefined tasks and evaluation metrics, meaning that the whole evaluation protocol is consistent and easily reproducible between studies. Also, we provide an online leaderboard allowing for continually measuring the progress in the field and also reporting the performance of new methods. Yeah, and finally, our current and future work, let's say for the next year, is actually to develop a model that can decode complete molecular structures based on our DREAMS neural network proposed in previous work which I had just introduced. Yeah, so that's all from me. Thank you for your attention.